Welcome to Computer Science 305, and today we're talking about the second look at Java. And so, in this view, or in this lecture, better yet, would be that we're looking at, basically we're going to start talking about polymorphism, right? The object, we're kind of getting into the object-oriented constructs within Java. And so, subtype polymorphism, which we described earlier when we were talking about ML, is something that is inherently built into Java, right? So we look at this line here where we just declare a variable x of type person, right? And so we ask ourselves, right, does this declare x to be a reference to an object of the person class or not, right? And in reality, it's not exactly a reference, as we would normally think of it. Because person itself actually can possibly be references to many other objects of many other classes, right? So x is not only a reference to that, but it's a reference to all the things that person itself can reference, right? So, but in this, person can also be many other things, including all the subclasses of type person, right? That's what x can be. And so in this, we know that Java has subtype polymorphism. So in order to talk about this, we actually have to talk about many different things, right? We have to talk about interfaces and how we implement them, the concept of extending classes, the difference between extending and implementing, and then we get into the whole construct of multiple inheritance, and then finally we'll end with generics. So interfaces, right? So in other languages, we have this notion of the method prototype, right? It's the thing that just, if we think about in C, C++, it's what we talk about in the header where we describe the actual definition of the function prior to we actually implement it in the .c file. Here in Java, we can actually create interfaces which describe what I would call more of a public contract, right? In an interface, all methods are known to be public and abstract, and thus they must be implemented by any class that implements this interface, otherwise that class must be abstract. And so this means that these methods show up as a part of the default contract or interface to any class implementing that specific interface, meaning then that we can guarantee that these will be there. Furthermore, we know that it's always better to point towards the abstract, in this case, or the least interface that I need. In this case, it would be the interface drawable, knowing that I can always gain the show and hide, and allowing the actual implementation details of this to be in some low-level concrete class or a part of the actual inheritance hierarchy. So what we can think of then is that if we consider these public abstract methods to just be prototypes, right, because they have no implementation, then an interface becomes simply a collection of method prototypes. And this is true all the way up until Java 8, which allowed us to do some more interesting things. And Java 9 has some more significant changes. But we're not going to get into those. The very basic construct of an interface is what we show here, right? So we have this public interface drawable. Has two things. It has one where we show the actual item that can be drawn, right, at a given coordinate. And then we can also hide that item. And so whatever that means will be based on the implementation that is provided. So when we get into implement interfaces, right, a class can declare as that implements a particular interface. Actually, it can declare that it can provide multiple interfaces, right? But when the second it does that, if the class is not abstract, it must then provide those same public method definitions that match those defined in any interface it implements, or its superclasses implement. So we need to bear that in mind. An example of this would be the class icon, right? Icon implements drawable, and that means that we have to then provide a show and a hide method, and then any other methods that icon itself needs. Similarly, we can do this with square. Square, we can have drawable and scalable, whatever scalable means, but now we have to have both interface, the methods of both interfaces as a part of the class square. So the question becomes, well, why would we ever do this, right? what is the whole point of this? Well, we know that an interface can be implemented by many classes, right? So, for example, we can say a window, the mouse pointer, and oval. They're all implementers of drawable. But the beauty of this is it allows drawable then to become our reference, right? We can then create many different instances of drawable, but they can all be one of these different potential drawable implementers like icon, oval, window, mouse pointer, etc. But now we know that for any one of these, we are guaranteed that they must have the two methods that we care about, show and hide. And this gets us into a design principle, which we call design by contract. And so in object-oriented systems, we want to always ensure that whenever we're designing these software systems, that we, one, define a clear and minimal public contract, right? That's what the contract part is. And then we want to always utilize that contract itself, right? The most abstract version of it. So in this case, the interface in Java as the type for our variables. And then we'll utilize polymorphism, right? Subtype polymorphism in this case, as our way to sort of control the implementation, right? Our variable points to a type of drawable, but that drawable in this case could be an icon, and then a little bit later it's an oval, and then a little bit later it could be a window or a square or a mouse pointer. It can be a whole bunch of different things. We never had to change the type of the drawable D, right? We changed the implementation of it. This becomes there's another design principle that we're using here, which is called the dependency inversion principle, where we always point our thing, like in essence, where any class that we have should always hold a reference to the most abstract types of an inheritance hierarchy that we can. In this case, drawable. Instead of creating variables of type icon, one of type oval, one of type mouse pointer, one of type window, we can just have one that is of type drawable, and then it can be swapped out to be any of those at any one time. This is a basic use of polymorphism in a basic good design construct. So polymorphism without interfaces, right? There is ways to do this without interfaces. They're a little bit more difficult, but basically you just have more or less abstract classes where ones are essentially becoming interfaces without actually being interfaces. But anyway, so let's say we have some methods, static void flash off, right, which takes a drawable D and an int k, and basically what it does is for each from I at 0 to k, all we're going to do is we're going to show D and then hide it, right? So it's going to flash this drawable for a certain period of time, right? The class of object referenced by D or to by D is not known at compile time. We can't know at compile time what actual type D will hold. All we know is that for now it holds something that implements drawable. But we also know, as I've been saying, that has the show and hide methods, and that those are defined or guaranteed that we can be able to call those. Right? They must be there, otherwise the system would not have been able to be compiled. If we want to work a more complete example, which I'm going to actually code up, we'll work with the work list interface for a collection of string objects, right? And the goal here is we're going to be able to add to, remove from, and test for the emptiness of the work list, right? So it's very basic. We're creating another list, just like we always have been, but it should form a pretty concrete example of what we can and can't do with these things. I'm hoping that everyone already understands these types of constructs, but just in case, we'll continue going through, right? And this will connect in with the next lecture on object orientation. So we go ahead and we'll create the work list class, right? Or the work list interface inside of a CSCI 305 package. We'll call this work list. Make an interface, and that gives us basically what we need, right? So we have a couple of methods we'll implement first, which the first one is the void add string item, right? We'll put a little comment action in there. So we can add one string to the work list. And takes the parameter item, which is the string to add. Pretty simple concept. We have a second one, which is the has more, which simply tests whether there are more elements in the work list. That is to say, it tests whether more elements have been added than have been removed. So in other words, is it empty or not? So returns true if and only if there are more elements, right? So if there's something beyond what we've already seen. So, so we create that, returns a Boolean, has more, good to go. All right. So then we also need to be able to remove, right? So we have last method, which simply remove one string from the work list and return it. There must be at least one element in the work list. And that returns the string item removed. All right, very good. So now we have this interface, right? It guarantees that we have these three methods in anything that implements work list. And so interface documentation, right? Comments are especially important when we are defining the interface, not as mainly because they give us the capability to define exactly what we want the implementation to do. So more importantly here than anywhere else, assuming that you use interfaces when you're building your code, that you should provide this documentation or for others to implement based on that, right? So the work note that the work list does not specify how this must be ordered, which means we could easily utilize this in using a LIFO or a FIFO approach, which is a stack or a queue, or even utilizing, for example, an ordered binary tree or an ordered set. Lots of different approaches could be applied here. All that matters is that we have the capability to add, remove, and check if it's empty or not. In this case, we're going to implement it as a stack using linked lists. So we can, first off, we need to create our friendly node class as always whenever we create these linked data structures. And so node is just an object that holds a string and a link to the next node. It can be with that, it can then be used to build the linked list of strings. And so, as we stated, it has simply the string data, so private string data, right, which is the node of the string, right? Sorry, each node has a string. And we have the private node link, right? Which is obvious links to the next node. Finally, we have create constructor. The constructor simply is going to take in the two parameters that are the basis for this entire class. So we do that. Oh, sorry, the data. Let's see if I can format this. Apparently not. So I'm going to start fiddling around. Public node, and so we take in the data and node the link, right? Okay. Then we need to have a few things, and a couple of accessors so we can extract the data as necessary. Note that when we don't have setters for this, and the fact that they're private, so the data has been fully encapsulated, this is going to make the node immutable, right? We can never change it once it's been created. So we have an accessor for the string. Which returns our string item. And then finally we have the accessor for the link, right? All right, looks good. Okay, so that's been done. Next thing, we need to create the stack. So we go ahead and we'll create the stack class. Right? So simply a stack is an object that holds a collection of strings. Pretty simple. Very basic data structure. And all we have to do is create the top node and set that equal to null, right? Because we assume that initially the list is empty. And then what we're going to do is we will create the few methods that we need. So typically a stack has a push and a pop method, but we'll call this add and remove, I'm guessing. Which takes in, so if we add, that takes in a parameter of data, which is the string that we're going to add, right? So public void add string data. And the whole goal here is, oh, sorry, we have to actually implement, so that makes sense. Yeah, we implement work lists, right, which gives us that capability to set everything up so we can easily implement the methods necessary. So I already added add, so we need has more and remove, so we'll add those in. Probably put the add override. And anytime I override something, I don't like to have documentation because I like to use the documentation that was provided initially by the original definition. So we'll talk about how to deal with that, and the typical way I deal with that is by creating without doing this, I like to say in curly braces at inherit doc, which if I was to generate this, it would just simply inherit the documentation rather and replace the curly braces and anything inside of it with the inherited documentation rather than actually utilizing what is provided here in the notes. This is, in my opinion, a better way of doing things and more coherent with practice rather than what is being laid out in the book. Alright, so our add method is simply going to add a new item, and then it's going to use the link of the current top, right? So now we're pushing onto the top of the stack the new data item by constructing a new node linking to the previous top. Then all we're going to ask is for our has more, just question whether or not top is equal to null. And if it is, then we're returning the checking if it's not equal to null. If that's true, then we have more, otherwise we don't. And then finally, we will go ahead and finish remove, right? And this we need to pop off the top item, right? So say node n equals top equals n.getLink, and then we return n.getData. data. Pretty simple, right? We note that this should only, it says in the documentation here that this should only be called if the stack is not empty. It does not say it checks if the stack is not empty. It just and so that would be something we would normally do. We would first check if the stack is so if has more returns false, then we would throw an error. Otherwise, we would continue on. In this case, we do not do that, probably for simplicity's sake. So, moving forward. Let's create a quick test of this, right? So we'll create a nice little driver class for us to operate this with. And we'll create a public static void main. And then we create a new work list. We'll call it W, and we say W equals the stack, a new stack. And then we're going to add W.add the plow. W.add for gives space, and W.add the cutworm. So then if we say system.out.print w.remove system.out.print w.remove and system.out.println w.remove, right? And we should see the expected output. The cutworm forgives the plow, which is lame, but regardless, we'll run that, find out what happens. And we see the exact same expected output. Works well. Very good. So you could actually have other possible implementations, right? We could obviously use a queue, priority queue, a straight up linked list. As I said, a ordered tree, a whatever you want to do. Lots of different ways of thinking about this. And then, of course, you use a tree, many different ways to walk that tree for that order. So you could have lots of really good stuff going on here. All right, this brings us into the next topic, extending classes. All right, so now we've talked about how do we implement interfaces. Now we need to talk about the next part of subtype polymorphism, which is the extension of classes, right? So this is a far more complex concept of polymorphism. Before, what we had was just the capability to define what is the contract through an interface, and that says here are the methods that must be part of any class that implements this. Whereas instead, we can now derive one class from another, right? We can gather, and this kind of brings in that whole concept, if we recall from when we were talking about polymorphism in the first place, which was that a subtype is a superset of the supertype, right? And that's because when we do extend a class, right, using the extends keyword in Java, we're actually gaining any public protected members of that supertype as a part of our current type that we're creating. So now, if we create this class called peekable stack, right, which is just like stack, but also includes a new method called peek, which allows us to examine the top element, it not only will have all the previous components of stack here, right, because they're all public, but we'll also have this new method as well. So this gives us the capability to vastly expand, right? And this kind of gets into another design principle from object-oriented concepts, which is called the open-close principle, right? Anytime we create a system, once we've created a class and it's been tested and vetted and it's good to go, we know that we now consider it to be closed to modification, but open for extension, meaning that we can always specialize more and more, but we leave the more general classes alone over time. So bear that in mind. Almost all the principles we talked about so far are part of very basic concepts of object-oriented programming, things that you should go look up and read about. Anyway, so we'll create the peekable stack. Pretty simple. So in this, we're going to extend stack as it shows here, right? We're going to extend the stack class, giving us the capability to only have to add that which we need, which is the peek method, right? Assuming that we inherit, right, everything else. And inheritance only applies to, in Java at least, only applies to public and protected, protected and default visibility items, and the default only applies if they're in the same package. So bear that in mind. But private components will not be inherited as a part of the actual extension. So we'll make our little documentation here just so we can stay good to go. So we have peekable stack is an object that does everything a stack can do. Maybe I'll spell object correctly. And can also peek at the top element of the stack without popping it off. Okay, good times. So, very simple. We create the method peek. Which basically says examine the top element. This should be called only if the stack is not empty. Yet again, if we were to implement this in a professional way, we would always do a check to validate that the stack is empty or not, and then throw an error if it is empty rather than allowing just things to happen. Because basically what would happen is it would cause a null pointer exception. That's not a good thing. So we get the string, right? So this is what's going to happen is instead of actually allowing us to really do a peek, we're going to pop off the top item, and then we're going to add it. So that gives us string s, right, when we pop or remove, and then we're going to re-add it and then return s. It's a deceptive way of doing this, but it will work. All right, so now we have peek, good to go. If we go, now we have to understand this is, as I've been mentioning, this is all about inheritance, right? So because we have to think about this, because peekable stack extends stack as stated here, right, in the code, it inherits not all, but in this case, it inherits all the underlying methods, but not all the fields, right? Because node, the top field is defined private, so it does not directly inherit that. It has no access to top. So we have to have some other way of dealing with that. We cannot access it directly. It technically inherits it, but we can't access it. So beyond that, we also have inheritance. Inheritance is a side effect of polymorphism. But in this form where we are doing extension-based polymorphism, but we also have the capability now to use peekable stack wherever we can use a stack, right? Because it extends stack. But now we can also use peekable stack anywhere we can use a work list. So now let's go back to our driver, and we'll create a new stack. We'll call it stack s1 equals. And I'll scroll down so you guys see that. Stack s1 equals new peekable stack, right? And peekable stack s2 equals new peekable stack. And we say s1 dot add drive, s2 dot add cart, and we'll say system dot out dot println s2 dot peek. So now. Oh. So interesting enough, right, as it says here, we should note that you can't call peek on S1, right? Because S1 is defined as a type of stack. And then if we look inside stack, there is no peek method, right? But there's a peek method defined in peekable stack, even though that's what it's implemented as, right? So it's actually S1 holds a reference to a type peekable stack, but it only knows the type that its type is of stack. So it can't actually operate that method, right? We'd have to do a downcast into pickable stack to be able to call that. So all we can do is work the add, remove, and has more, whereas in S2 we can also use the operation peek. So if we were to run this, right, and then we can actually verify that. Say S1.peek. Oh, that will fail. The only way we could actually do this is if we add, we'd have to essentially do the cast to peekable stack. So we can do it, but it would be more annoying than anything else. We'll go ahead, run that just so we can verify. And we get cart, right? Because that's the only item that is in S2. And but it gives us the validated output that we expected. Okay, so we go back and we know that we look at our peekable stack, and as I mentioned, this was kind of a weird way of doing this, and it even says that this is inefficient, right? Basically, we had to remove the item and then add it again and return the item essentially the string value from the removed item. Well, the reason we had to do that is because as I mentioned before, it does not actually inherit the capability to use top, right? Because top is defined private, and so that's the reason why we could not just say return top.getData. So how do we get around this, right? Well, what we could do is we could actually use the keyword protected, right? So protected means only items within the inheritance hierarchy have access to this particular item, right? This field or this method. So anyone who extends this class, at that level or below, right? So this class or anything that extends that class has access to it. So essentially, if we go back to stack here, we call this protected. Then what we have is now peekable stack. We could re-implement this to say literally return top.getData, right? And we can see that, yes, it now works, right? But if we were going to go back to stack and we make that private yet again, right, and we go back to peekable stack, it now throws an error because there's no access, right? Top has private access. So we have to go, so that means private means it is restricted to that class and that class alone. Protected means it's restricted to that class and any of its subclasses. And then there's, if I can also remove this, right? And this is called default or package private access, which means that, or package protected access, which means that essentially anything in that package, so in all of CSCI 305 package, all of these classes can now see top, but nothing outside that package, including sub-packages of that package, can see it. And then finally we have public, which just everything can use it. In the case of inheritance, we should always use protected, as it is the, well, in essence, we should always use the most restrictive access modifier that we possibly can. In this case, using protected is the best bet, given that we want to inherit from stack. If that wasn't the case, then we would leave it as private. Anyway, we go back to this. We can rerun the driver and verify that the new implementation works correctly, as we see. So it's always whenever we are designing anything, we should always be aware that there's a potential for reuse and inheritance. But if you don't have anything directly inheriting at this exact moment in time, or don't foresee it immediately, then maintain your variables as private. As things change over time, always be able to refactor and adjust that access modifier as necessary. So there's also inheritance chains, right? So a derived class can have more classes derived from it, right? All classes but one are derived from some class. So interestingly enough, in Java, all classes except for the base one, which is object, are derived from object at least, right? Or some other derivative thereof. So object's the base class, and it's the one that is the necessary, most fundamental concept inside of the class hierarchy, right? An object itself, so if we were to go and look at object, I believe we can actually, let's say java.lang.object. So if we were to say just object X and we actually want to look inside object, object has a whole bunch of business going on, a lot of native stuff. But it has a lot of the basic functionality that we expect. For example, get class. And note that almost all these are called native. So native is a key word that tells us that it links to some underlying code, like that was written in C, that is the basis for the actual language system itself. So we have get class, which tells us the type of the, which actually gives us a class-based object that we can then do reflection with. We have the base hash code method, which is used for evaluating the underlying equality of a object, right? So if you go implement equals, we should always implement equals and hash code together. Then there's the equals method. There's a whole bunch of other ones. Clone, so you can make copies. ToString is defined, which note is an actual definition in Java, as opposed to an actual implementation of the in native code. And then we have notify and notify all, which are used for threading. And there's a few others. Wait, also for threading. Let's see, what else do we have in here? Oh, and then finalize. Finalize is the destructor. So finalize is called whenever a class is cleaned up from or deallocated from the heap by the garbage collector. So if you have anything that needs to be done, like for example streams that need to be closed out, etc., you should put those in a finalize. So you should override finalize and then be able to clean up your mess. So anyway, that's a quick overview of object. I would suggest go read about it in your spare time. But so basic constructs. So you can always override inherited definitions, right? So anytime the sole goal of inheritance is that we are always, whenever we extend a class, we are making that a new version of the class that's more specialized than the previous. And so we always inherit any public or protected members, so methods or fields, of the class and any other classes above the one that we're creating in the inheritance hierarchy. And that means then that there was all this code that was written before. Now, oftentimes, you want to be able to, beyond just creating new, like you're implementing an abstract method, beyond just creating new code, sometimes you need to actually utilize the previous existing code. You may need to totally override any previous behavior, like, for example, the way if you're implementing the stack using a tree-based implementation, maybe the way it was handling things is not going to work quite as well as you wanted to, so you need to just scrap everything that happened before. Anyway, so there's lots of different things we can do. So, for example, we can override the toString method, right? Which typically just creates a combination of class name and a hash code, right? For what we looked at before. So if we were to run this piece of code that they're showing us here, which is system.out println, and let's just use S1 rather than new stack. If we were to run this, we get this nasty peekable stack at, and then some numbers, right? What we'd rather have is a nicer string that actually tells us something. So we can go into stack and create a toString, right? And actually, I'm just going to override that really easily. So as we can see here, we can override all these methods from object. We'll choose toString, and we simply return stack with top at plus top, right? Now, this will lead us to a smaller problem, right? What is the definition for toString for node? But so we'll run that and see what happens. And it gives us the same problem, right? Because we get the node at some annoying numbers. So now we have to figure out how to deal with that. So let's go ahead and implement the nodes toString. And what we'll do is we'll just simply return the data. And then if we go ahead and run that one more time, and then maybe what we should do is return in quotes so that looks somewhat decent. And it is, oh, yeah, there we go. Okay, so now it'll come out that it actually shows, you know, stack with top at the string drive. So that looks a little bit better. So if we think about this, inheritance forms a hierarchy, right? It's basically an object tree, if you will, with the top being object, right? So all classes that are loaded at any one time in the Java virtual machine. So that would be any classes that you use, like in this case, if we look at driver, right? So here we've used work list, stack that we created, system, and then whatever system has inside of it, stack, so peekable stack, and then string will be in there. So that, and node, and let's see what else does node have. Yeah, so node and then string, of course. So all these things. So we have a whole bunch of stuff from java.lang. So anything that all those extend all the way back up to object will create this giant hierarchy, all extending out of object, right? The other interesting thing here is that we also sometimes think of inheritance as one useful class extending another, right? Which kind of is in that concept where often when we get into specialization, right? For example, we can create a very slick quicksort implementation that then we realize perhaps what we might need to do is refine that so that instead of always using quicksort recursively all the way down, maybe we have a better implementation that does that same thing, except for when we get down to, I don't know, let's say 8 items or less, we use insertion sort. These are just very simple ways of adjusting the algorithm, but that would be a specific extension to that quicksort algorithms class. We can also use inheritance as a way to factor out common code, right? So let's say that you built a hierarchy of objects and you started noticing that a lot of them use the same type of data. You define the same methods over and over. What we could do is, instead of having the same method across multiple concrete classes, we can actually pull that method up into the more abstract part of the hierarchy, or create a new intermediate node above those, right? A new class that is a superclass of ones that share the same method, and we can leave it there. So now we only have it in one place, right? This is a sort of that concept is actually called refactoring, but the basic notion that this is an implementation of is the design principle, the DRY principle, DRY, which says do not repeat yourself. So we should only implement anything one time, and then we should figure out how to share it among and reuse it among all of our classes if necessary. And so one of the things that we can think of is, like, look at these two classes here. We have label and icon, right? And in these two classes, they're obviously not connected to each other. But what we start seeing is that we have a lot of the same stuff going on. We have private int xy, int width, int height, right? These are all common fields across both label and icon. We start seeing that we have move, which has new x, new y, which does the exact same thing. The only difference here is the private string text, private GIF image, and private string get text, and private GIF get image, right? These are the only two things that change. Everything else is the same. And so what we want to really do is we want to extract out all the common elements and then construct an abstract class. Now I'm going to actually do this to show you what this actually would look like in practice, right? So let's create these two items. Okay, label, which has the private int xy, private int width, and private int height, and we have private string text, and then public move. And then finally we have the string, right? Get text. And then we need the other class, icon, which has all the same stuff. And then private int width and private int height. And then the private GIF image, public void move int new x int new y, which says x equals new x, y equals new y, and public void public GIF get image, right? Okay, and we'll go ahead and just create fake classes for these, for that and text. Oh no, that was fine. Okay, so now that we have that, what we notice though, as we said before, is we can actually extract out things that we know are common, right? So this is called a refactoring, and we can actually call extract, and we go down to, I believe, we need to pull up. We need to pull members up, right? So we can actually do that, right? We need to actually create a secondary class that we're going to make common to both label and icon. And so we'll call this, and I believe it's called graphic here. Yeah, so we'll call it graphic. And so we'll go and say label, and both label and icon extend graphic. And same with icon. And then what we want to do is we want to pull members up. So we'll go ahead and say refactor, and then we'll do the pull members up. And the things we want to pull up are move and XY and width and height. And then everything else we said was the same, right? And we say refactor. And then now if we look in icon, it only has the stuff that icon needed, which was the GIF image and the get image. And we're going to look at label, and we have to do that same thing, right? Because apparently it didn't want to play. So actually if we go look in graphic, it has everything we needed in graphic, so we can actually delete all that from in here because we don't need it. All right, so we look at graphic, it has all that stuff. We'll maybe make these private or protected. So we can actually use them. And now we have everything good to go. It tends to be a little bit easier if you are more familiar with your actual refactoring tools. But now the common code data have been factored out into a common base class as expected, right? And these are some basic techniques, right? That we should all know how to do. So when you write the same, so basically this is getting down to the same problem. Whenever we start writing the same statements repeatedly, we should stop and think, what should we do? Well, we need to refactor this out. We need to pull this type of these common things out and put them into some sort of base class or place in which these things belong, such that we can reference them rather than rewriting them over and over and over. One of the problems that happens if we keep doing that is that we will make a mistake. For example, if I had like 4 other classes along with label and icon all using these same base things, the problem becomes is, well, what happens if I need to make a change? Like, I was wrong, and I know that they all are using the same thing, right? But what if I was wrong? What if instead of being in a 2-dimensional system, I actually need to be in 3 dimensions? But I forgot to make a change to one of the items, and so now all but like icon have the 3-coordinate based system in 3 dimensions, rather than and then icon only has the 2 dimensions still. Well, that becomes an issue and will probably cause some sort of weird error because I forgot to do that. Instead, what I could have done is just had this graphic construct, which then I can make one change one place and it affects all the classes the same. That's one of the real beauties of using inheritance in a polymorphic object-oriented system. Let's see. The real trick, I guess, would be that we need to see the need. Yes, start noticing this. To see the need for a shared base class early in your design, rather than well after you've been writing everything and you need to do the reorganization. Although, knowing that we have techniques like refactoring available to us, we can escape that problem as well. So, bear that in mind. Subtypes of inheritance, right? So a derived class is a subtype, right? And I remember I mentioned this at the very beginning of this. A subtype is a subset of the values, but it can support a superset of the operations. So basically, a subtype is a superset of the supertype, if we want to think about this. So when we design in class hierarchies, we need to think about inheritance of functionality, right? So if we have a figure, a polygon, which is extended by polygon, which is extended by quadrilateral, which is then extended by square, we need to ensure that what we're building here actually makes sense, right? And even though a reasonable and intuitive hierarchy has been designed, it does not necessarily mean that it will function as we expected. So this kind of gets into a difference between the concept of there's a finer grained concept of object-oriented design, which is called favor composition over inheritance. And whether or not I talk about that at the end of this will be dependent on what we talk about, but I think I'll save that for the object-oriented lecture. Anyway, so I'm going to stop here, and then I'll start again at the next part of this, mainly because it's been a whole hour.